right, so now we are going to talk about excitation of surface plasmons. So here's the problem. We learned that a surface plasmons have higher K vector compared to air, right? What that means is that now, due to this high, mismatch of the momentum, there's no way to excite surface plasmon at a plain metal dielectric interface. So what does that mean? Let's say you have a metal here, and then you have a dielectric here. And let's say you are working at this frequency. And then imagine you shine light from the top like this. Okay. And then this, let's say this defines your lambda. And then what you want is the surface mode with K vector larger than this. So what you want is surface mode with let me draw surface mode like this, and then this is your lambda p. Okay, so lambda p is shorter than lambda 0 in this case. So now you imagine you change the angle of incidence, for instance. Is there any way that the in-plane K vector of free wave can be matched to the K vector of the surface plasmon? That's impossible, because let's say in a extreme case, you shine light almost 90 degrees. In that case, what you have is like this type of wavefront, right? You shine light in this angle. And then the space difference between the wavefront is lambda 0, which is still larger than lambda p. What you want is the mode looks like this, whose lambda p is smaller than lambda 0. So no matter what angle you shine on, there's no way to match the phase of these two modes, right? And this is basically because you have your plasmons are much higher, having much higher K vector compared to air. So if you have a plane interface and shine light, whatever angle you shine light on the metal dielectric interface, it is impossible to excite surface plasma. Okay, then how do we excite surface plasma? How do we solve this problem? Well, one brute force way to solve this problem is just not using light, but using electron. As I said, if you have a metallic interface, you just shoot electron, high energy electrons. And then these high energy electrons scattered and creating the surface plasma. And then this high energy electron, of course, has really high K vector. So it can excite any sort of plasmons. And then by measuring the difference between the incident energy and the outgoing energy, you can see how much of energy this electron loses, right? And that energy actually is associated with plasmon energy, right? So if you have a kind of thin slab of a metal, there are two ways that this electron can lose its energy. One is exciting a bulk plasmon, and the other is this electron excites surface plasmon. So you can see here, if you actually look at the electron energy loss spectrum, there's two peaks. One is from the bulk plasmon and then the other from the surface plasmon. And then of course there are multiple other peaks because it corresponds to 2 bulk plasmon, 3 bulk plasmon, and so on. Okay, but anyway, this is a kind of a brute force way to excite surface plasmon. And this is actual experimental data, which I don't want to explain in detail, but the message is the same. Like it's just, you just shoot high energy electron and then measure the input and output electron energy and momentum, and you can map out the plasmon momentum and energy. So that's how you do it. Okay, but we want more, how can I say, elegant way of exciting surface plasma, like full optical way of exciting surface plasma, other than shooting electrons using electron gun. So the idea is basically using one idea is basically using a high index medium. Okay, so let's say you have a plasmon at air metal interface. Then that plasmon has this red dispersion relation. And then you can imagine you have high index medium. And in that high index medium, just a regular free wave have this type of a low slope light line, right? So the surface plasmon of air metal interface and the free wave in a high index medium actually has a intersect phase matching condition, right? But this is very conceptual, right? This is just, I just draw a dispersion relation, and how to implement that? That's the real question. Like, how can we actually create the system that that we can actually use high index medium? So the way you do it is using Prism. So I will go through like multiple ways they can use that you can use this high index medium. So one way is using Prism. Okay, so here the configuration is like this, called Otto configuration. So you have a prism here, high index material, and then here's a gap. Here's a gap, and then you have a air metal interface. Okay, then at the interface between air and metal, the plasmons are roughly following this red curve. Whereas in the prism, the index of the prism is large enough so that its K vector can be even higher than the K vector of plasmons. So if this condition is met, then you can actually change the angle of incidence. You can basically engineer the angle of incidence of this light inside of prism so that their X component, their surface parallel component, and the propagation constant of plasmon are matched. Okay, then the phase matching condition is satisfied so that you can actually launch plasmons. Okay, so here's one way to use high index medium. And similar approach can also be applied on the other case, like what is called like a Kretschmann configuration. And here the prism is on the back side, but basically it's the same. So you have this metal have two interfaces, of course. The top interface is the air metal interface, and the bottom interface is air dielectric interface. And if you compare the air metal surface plasmon, and the dielectric metal surface plasmon, and also the free waves in a prism, then they have this type of relation. So the metal dielectric surface plasmon has longest K vector, and then free wave in the high index medium is the second, and the third is the air metal surface plasmon. But anyway, the same way, like if you change the angle in a certain manner so that they match to the propagation constant of air metal surface plasmon, then you can excite the surface plasmons at the air metal interface. But of course, there's no way that you can excite the plasmon at the metal dielectric interface, right? Because metal dielectric interface K vector is always larger than this value. Okay, so Chae-Yoon asks, are we assuming that we are using monochromatic waves? I wonder what happens if we don't use monochromatic waves. Yeah, here we are assuming that we are using a monochromatic wave of omega defined by this, omega E, excitation frequency. And then if we don't use monochromatic wave, I mean, you can basically do the same thing for all frequencies and then combine together. So it's not like, there's nothing special. Like if you use broadband light, then you basically do this calculation for all the other frequencies, and then the linear combination of them will be your solution. Yeah. So here's a few notes. So first, we can, by using this technique, we can excite surface plasmons from free wave, right? But that means surface plasmons can also become a free wave because it's, the physical phenomena is reciprocal. So if we can excite surface plasmons from free wave, that means surface plasmon also can become a free wave in the same system. So in that sense, we call the surface plasmon to be leaky. So it leaks out its energy to the free space. Okay. And also, and then, but these are the details. But anyway, the imaginary part of the beta. So basically, so surface plasmon constant of prism metal air system and simple air metal system. So if you compare prism metal air system and then just bulk metal and air system, their plasma, if you actually calculate the propagation constant of these two cases, the plasmons of these two cases, they are actually slightly different, right? Because in this case, metals are thin, so that before it completely dies out, it meets prism. So there are this condition and then that condition a little bit different, so that propagation constant of these two cases are different. So this difference, the imaginary part of this difference is actually defines the damping rate of leakage radiation. And then imaginary part of the original plasmon defines a non-radiative or absorptive decay rate. Okay, and then when the radiative and non-radiative decay rates are equal, we get critical coupling, and we get the maximum coupling efficiency. So let me explain this a little more hand-wavy way. So it will become a little more obvious if you look at this. So so this is actually the result of an experiment. So this is the R, which is defined as a reflectance of a metal, okay? And then here is the K parallel of this K vector, normalized by plasmon propagation constant. So K parallel is again, K parallel is here NK0 sine theta, right? Divided by beta. So this is nothing but normalized sine theta. So you're basically increasing the angle from one value to some other values. So what you're doing from here to here is you basically shine light like this to shine like this. So you're basically increasing the angle of the incidence. And that's what you're doing here. And then when your K vector, the in-plane K vector, match to the propagation constant of beta, then you can see here reflectance becomes minimized. What does that mean? Most of the light is absorbed by exciting surface plasmons. Okay, so light energy is actually went to the surface plasmons. Okay, and then here, what determines the depth or like absorbance, absorptance of this reflectance dip is the ratio between this and that. Again, gamma leakage radiation and gamma material absorption. So you don't need to fully understand this, but what I want to convey to you is that in this configuration, as I said, these plasmons can lose its energy in two manners. First way is it loses its energy by radiating a leakage radiation, right? So as it propagates, it leaks out some light. And this is called radiative decay channel. Why this is happening? Because you can shine light to excite surface plasmon. So the opposite process, it should be also possible. So this is one way of losing its energy. And the rate of doing so is called gamma LR, leakage radiation. And second way of losing its energy is that because metals are lossy, right? Metals are not perfect, so it's always lossy. So as it propagates, it loses its energy due to material absorption, right? And that rate is called gamma ABS, gamma absorption. And the maximum absorption, maximum absorption occurs when these two are equal, which is called critical condition. I guess you are familiar with this concept, right? Like if you, the condition, like the critical damping condition is actually very, very fundamental thing. And you probably learned this in the elementary physics class in your freshman period. Or if you are in mechanical science, in mechanical engineering, you're probably even more familiar with this concept. So if a radiative decay rate and the absorptive decay rate are equal, the system is in the critical coupling so that maximum absorption occurs. Why that's the case? It's kind of difficult to explain in detail. So I just recommend you to just look up the internet. You can just use the keyword critical coupling, then everything will appear. Okay, so another way to use a high index medium is using a high index medium is using combining the system with a microscope and high index oil. So you can see here, if you have a silver film and then you want to excite surface plasmons at this interface, then instead of actually using Prism, you can just use a microscope and high index oil to match the phase. right? So that is also possible. So you know, and it's more handy in terms of experimental complexity. So you can also do the same thing as for P polarization, which is TM wave. You can see this is the input beam. So input beam actually launches surface plasmon, and you can see the plasmons are propagating. And if you are in S polarization, which is TE polarization, there's nothing. So you can actually image this thing. So here's the actual experimental data, and then where to use it, where to use Prism coupling. People actually use Prism coupling to determine the thickness of the film. So because this coupling condition is very, very sensitive to the phase matching condition. As I said, this peak only occurs when beta is equal to K parallel or NK0 sine theta, right? And then this beta, the propagation constant of plasmons, actually changes as the metal thickness changes. It also slightly affected by metal thickness. So it's very, very sensitive. So as you change the metal thickness, your beta shifts in a very small amount. And then that small amount can be detected by in an angle spectrum, because beta has been shifted. In order to match the phase, your theta has to be also shifted. So you can, if you measure the reflectance as a function of excitation angle, depending on the thickness of the metal, in this case, it's not the metallic thickness, it's the thickness of dielectric on top. But anyway, it's very sensitive, right? And then you can also create sort of a molecular detector using the same technique. So here, what this says is that you have also the prism coupler, and then depending on, so you basically flow like, so you have a prism, here, and then you allow this liquid flow above this surface. And then if this is a pure water, and then it has a very small amount of glycerin, and then as you increase the amount of glycerin inside the water, its index changes by very small amount, right? And that affects the propagation constant of plasmons, and also that affects the coupling condition. So if you actually measure the reflectivity or phase of a reflected light as a function of incidence angle, then you can see it's very, very sensitively changes depending on the index difference due to the inclusion of other molecules. So this is a kind of typical way of using surface plasmons for detecting molecules. And you can also think of fiber coupling. This is also a category of using a high index medium. So here, what is happening is that instead of using prism, high index prism, you use high index optical fiber. So the modes inside the high index optical fiber, here silica fiber, for instance, has a relatively high K vector, so that you can launch plasmons using optical fiber. So same technique. So in order to, so we began with this problem, the phase mismatch between the free space light and the and the surface plasmons, we introduce high index medium to solve this problem. And there are many variations can be possible, like in terms of actual implementation. You can introduce Prism, or you can even use a high index oil, or even high index fiber. Okay, all these things are just examples of introducing high index medium to solve this phase matching condition. And here is a different way of dealing with this problem. But I guess I will talk about this later on Thursday. So now I'd like to take questions. So while I'm waiting for you to type in the questions, I actually, so what's left in this chapter is actually we are going to talk about other methods of for exciting graphene, exciting surface plasmons, like grating coupling, for instance, and also excitation using small objects, and then their applications. And finally, end fire excitation. So is there no question? Would there be any? If there's no question, because we don't have that many materials to cover, probably I just go ahead and then try to finish this lecture notes. Okay, Thomas asks, can you explain again why beta changes so much if you change incidence angle? What beta are you talking about? The beta is the propagation constant of plasmons, right? Propagation constant of plasmon doesn't change as you change the incident angle. So you change the incidence angle in order to match the propagation constant of surface plasmon, and surface plasmon's propagation constant has been changed due to the change of dielectric material thickness. So let me explain this. If I explain this again, so here in this case you have a metal, and then on top of it you have a dielectric medium. And then this dielectric film is very, very thin. It's much thinner than the decay length of a surface plasmon vertical confinement. So that surface plasmons basically feel this dielectric layer. And then as the dielectric layer becomes thicker, more and more portion of surface plasmon is actually included in the dielectric regime, so that their property changes. Right. So if you remember, let's say this is air light line, and this is dielectric light line, and then surface plasmon associated with air metal interface looks like this, and then air dielectric interface looks like this. And in this case, where you have metal dielectric air type of a structure, the propagation constant of plasmons are in between these two, right? It's not entirely air dielectric interface or not entirely air metal interface. I'm sorry, it's not entirely air metal interface, but it's not entirely dielectric metal interface. So as the thickness of the dielectric layer increases, the beta, the propagation constant of plasmons, changes from this to this value, right? And the shift in propagation constant is very sensitive to the thickness of dielectric medium. so that in order to match that shifted beta, depending on the thickness of the dielectric medium, the matching condition basically changes very sensitively. So matching condition defined by the incidence angle changes very sensitively. I guess that explains your question. Okay, Berkai asks, is the air distance between the fiber and metal or grating structure and fiber important in coupling? How much does it affect the performance? And is there a way to find the optimum? Oh yeah, this is really good question. Yeah, so yes, it affects a lot. So the question is like this. Like for instance, if you have a fiber, high index fiber, and then you have a metal air interface. So what you want to do is using the fiber propagating mode, high index mode, you want to excite surface plasmons in the air metal interface. So the question is whether the distance between the fiber and metal are important. And yes, it is very, very important because it determines basically gamma LR here, the one that we defined earlier. So let's think about this a little further. Like, as I said, the way that this plasma loses its energy, there are two ways. One is through material loss, gamma absorb, okay? And then, of course, this guy wouldn't change even though you change the distance between the fiber and metal, because most of the absorption is going to be occurred in just metal. So even though you change D a little bit, it wouldn't be too much altered, right? So gamma ABS is basically independent of D. But the leakage radiation, or in other words, in this case, the coupling between the fiber mode and the surface plasma mode depends highly on the thickness, because this coupling between these two modes are dependent on their field overlap. And then their field overlap, of course, becomes larger as D decreases. And then if D increases, like for instance, if your fiber is far away from the metallic interface, there's no coupling, right? So this gamma LR, or the radiative loss rate, is strongly dependent on D. So the key is to match your gamma LR radiative loss rate same as the absorptive loss rate, and finding optimal D that gives you that condition. So that's the key. But this is a really good question. Okay, so I guess there's no other question. I'll probably stop here.